I will introduce myself. I am a data visualization, data storytelling practitioner, which means I work with data all the time. I visualize science sometimes. I visualize other things frequently. And I teach data storytelling, data visualization, both on LinkedIn Learning. I have a class on data visualization and communication at the University of Vermont. I teach workshops. I teach this stuff all the time. I'm very, very passionate about it. And what I'm especially passionate about is what I'm going to talk about today, which is I want you to change your default position when you're visualizing really everything and communicating really everything, is to change your default position to no. So let me explain what I mean. First of all, when we're creating visuals, particularly for communication, I'm not talking about visualization for understanding our data or understanding our science. I'm talking about, again, focusing on communications. You have to realize that communications requires focus. And I have a series of 3 acronyms that I've developed that will help you think about what to focus on. They are terrible, awful, ridiculously bad acronyms, but they have a really pretty good shorthand, which is the QUIs, okay? And the QUIs rhymes with why, which is good because that's sort of what it's all about. And there are 3 of them, okay? So here's the first one. And this one's the most obvious one and the simplest one, but you can already see, terrible acronym, you don't even know how to read it or pronounce it, but there is a pronunciation, okay? Quitus, all right? Now you're not gonna remember that, but you're gonna remember what it stands for, hopefully, which of course is you have to know what your data is saying. You have to know what your science is saying in order to communicate it. This one is straightforward, that's easy, we can move on to the next one. The next one is quianth, also terrible, but an incredibly important idea, which most of us, especially if we're not trained professional communicators, we forget this one. And not to pick on scientists, but scientists are sort of at one end of the spectrum, tend to forget it the most. Don't hate me for saying that. But it's really, really important to think about our audience very strategically, very carefully, very thoughtfully. And it's not what they've asked you for. It's not what you think that they maybe want from you. It's what they actually need from you. Why are you communicating this to them? What are they supposed to do with that information? When you really think strategically about your audience, you're going to do a better job communicating with them, creating things for them. And I love this video because it's a really good reminder that when we don't understand our audience, we may design solutions for them that don't work. How would you design an ice cream cone if you knew your audience was going to eat an ice cream cone with their toes, right? So maybe we'd take a slightly different approach. That's the idea. Now the third acronym, terrible, Quirwitz, okay, probably the worst one in terms of pronunciation, you would never guess, but it's, along with quianth, the most important idea one of the most important ideas I'm going to communicate to you today. Quirwitz, and again, something shockingly that people forget to do 99% of the time. I made that number up, don't hold me to it. But you have to know what you really want to say. When you're communicating, again, this is about focus. What are you trying to say? And like, duh, that's the most obvious thing ever. But most people really don't take a step back and think carefully, thoughtfully, slowly, what am I actually trying to say here? We just rush to it. Here's the science, boom, throw it down on the page, create a poster that's 800 miles long, 8 million words on it, and people figure it out, right? No. You have a point of view. You have something you're specifically trying to get across. You have to really focus on that in order to accomplish your goals. Because when you don't, this is your audience, right? They will be confused, annoyed, questioning your credibility, and all the other things you might imagine. So the QUIs are critical. You have to focus. Once you have thought through your QUIs, they're like 3 legs of the stool. Once you have actually done that, now you can take your data, your science, whatever it is you're actually visualizing, and move on and think about how you're going to visualize it. That provides the context, okay, in order to help you make decisions. Now, moving on to the next step, making those decisions about creating visuals. I want to say one thing first. All design, all creation of visual things is essentially, you're constantly thinking about, you should be, creating information hierarchy. This is more important than this. This is even less important, this is even less important. That's your goal in design, is to communicate to your audience, look here, don't look here, this is less important, etc. We do this by where we place things on a screen or a page, the size, the color we use, typography, and other things, okay? But there's a really, really important concept in data visualization in particular, but really it applies to all design, known as pre-attentive processing. Human beings experience visual information pre-attentively, subconsciously, very, very, very quickly, before you're paying attention. And this plays out in a bunch of different ways, but if you understand your audience's pre-attentive response to visuals, you're more likely to be thoughtful about the design decisions you make in order to trigger a pre-attentive response to do what? To communicate that information hierarchy. And where does that hierarchy come from? The whys. Okay, so I know my data, I know what I'm trying to say, I know what my audience needs from me, great. I'm gonna try to say this is the most important thing, this is the least important thing, fantastic. I'm gonna use pre-attentive processing to do that. Now, as an example of pre-attentive processing, if I asked you to tell me how many 4s do you see in this block of numbers, no design has been applied, you can't do it, you certainly can't do it pre-attentively, subconsciously, quickly. But as soon as design is applied, you can subconsciously in a tenth of a second guess how many 4s there are. So this is what I'm talking about. Trigger a pre-attentive response with your designs in order to help your audience see the truth in your data. And I sum up my design advice with these 2 words. Simply do less with your design. Now, what I'm going to do next is I'm going to walk through a visualization. Oh, and by the way, yeah, my favorite quote of all time. I would have written a shorter letter, but I didn't have the time. Yes, this takes time, but it's really, really important time, very well spent. Now, what I'm going to do is I'm going to walk through a data visualization. I've taken this visual, which is a real visual a client gave me, and I've applied 15 steps to make it better, all in the spirit pretty much of do less. Let me explain what we're looking at first. This is showing us, this isn't science data, this is like software application data, but it doesn't matter. Whether it's science or not, same idea. What we're looking at is bars that show us the user volume for a software application, and these 2 lines show us the error rate as a percentage, the percentage of people who experienced an error using this software application, and the dotted lines are the benchmark. We want to be below those lines. Okay, so that's the data, that's what's happening here. Now, what I really want to do, if I had like a magic wand, I would give you all a special new magical key for your keyboard, you know, like an F key at the top, right? That you could just click and it would magically make your visuals better. I can't do that, but I'm going to hopefully leave a little mark, a little scar in your brain today that it's going to be sort of like this, okay? Like you're going to say, yes, what would Bill say? Yes, I'm going to do that, okay? So you're going to click on your little F key, which I'm going to show you in a second. Now, we look at this visual. What is the first thing I look at this when I look at this visual? The first thing I react to usually is, oh my goodness, I don't care about 1.23 million users, 49,223, whatever that is, 3.8%. None of those numbers are useful to me. I just need to know how am I doing. I need the gist of the data in this particular use case. So the first thing I ask myself is, do I need the data labels on every data point? And my answer to that, using my magic new keyboard key, is I say F no. F no to those numbers, get rid of them, okay? By default. Now, Bill, are you saying you can't have any numbers on any charts ever? Of course not. What I am saying though is your default position should be no. And you're going to see this is going to play out again and again and again, okay? Now, lesson there, remove unnecessary elements. Now, as I look at this again, I ask myself, what else now sort of jumps out to me, something I might consider changing? Well, this is a subtle one, but I look at those grid lines and I say, do I need grid lines on my charts? You can guess the answer. I say F no to the grid lines too. Remove them. You don't need them. Can you talk me into adding them back in occasionally? Yes. Am I going to make sure they're insanely light, faded back gray if I do include them? Yes, those really weren't bad, but by default, the answer is no. All right. So removing unnecessary elements once again. Now, after that one, I look at my axis labels. 0, 0.5, 1%, 1.5%, etc., 900,000, 1.1. Do I need all those numbers? F no to those too. I say, oh, so actually, first one is, why do I have my axis labels tilted 90 degrees? Sorry, let me show you that one again. My axis labels are turned to the left, 90 degrees. I have to crane my head like this to read them. I want to get rid of those, move them up to the top. I know Excel doesn't do that by default, but whatever tools you're using, more likely than not, they turn them on their side. Let's not do that to our audience. Let's help them read it. By the way, you're more likely to catch spelling errors if you actually put your labels horizontally where you can actually read them. So make things readable. That's the lesson there. Now, this is the one where I say F no to all those extra numbers. I would say for every chart, by default, give me the bottom number, the top number, nothing else. Again, can you talk me into adding more numbers in? Listen, it's really important to see 3.5%, or I need some distinction to see where the bars are. Maybe I need 4 tick marks instead of just 2. Fine, but your job is to talk me into it, not the other way around. By default, the answer is no, all right? Now, removing unnecessary elements. Now, once again, I go back and I say, all right, do I like the look of those bars? Those bars are becoming kind of distracting. And that design approach of the hard edge and the gradient of color, never even mind that one, is really not good. I say no to that design of those bars. Bar charts, a bar represents a single number. It should be a solid object. And are there exceptions? Are any of these things that I'm saying like absolute rules? Definitely not. But by default, I want to simplify the design of my visual elements to reduce visual distractions. And also that reduces the moire effect, sort of like wearing a striped shirt on TV. There's a vibrational disturbance when you have those hard edged lines in the stroke around these bars as they were originally shown. So I'm going to change those. Now, the next change for this one, and this is a pretty big one, is I look at those bars and I ask myself, what's the point of those bars? In this particular data story, this visualization, I asked the client, this is a real chart, and I said, user volume, do we care about those numbers? Right now, pre-attentively, the bar jumping up from December to January is one of the strongest components visually. It seems like that's important, there's something going on there. And the client said, yeah, no, we don't really care about user volume. It doesn't really have an impact on user error rate. Why are we showing them then? My next F no is I say no to the bars. They serve absolutely no purpose for this visualization. One of the things we tend to do when we're communicating with data is we say, well, here's all the data. Let me show you all the data. And we don't think strategically about whether it's actually useful. Maybe it's interesting, but not important. Okay, so we gotta get rid of that stuff. So next up, I look at this visual and I ask myself, now with what's left, pre-attentively, what is popping out at me? And I look at those dotted lines and I ask myself, should I be drawing attention pre-attentively, making those thick, heavy dotted lines? Those are the target error rates, the benchmarks against which I want to measure the actual data. The star of every chart is the data, not the benchmark. So I say F no to those lines. I want to simplify them dramatically. Now, you could argue maybe these are too simplified, especially for a Zoom presentation. Good, we can have a good argument about that. The long story short, by default, I need to draw attention to the data, the star. Now I look at the data and I said, oh my goodness, do you think that I like the markers that are on those things? By the way, focusing on what matters, all those dots along those lines, which sometimes our software adds by default, you know my answer that I do not like those markers, all of those lines. I'm going to reduce those or get rid of those if I possibly can. Again, you might say, well, now I don't know where the March data point is. Who cares where the March data point is? What would be the purpose of that? I don't need to know that. I can see kind of where it is. The gist of the story in this case is enough. And by the way, scientists, I get it. Listen, if you're communicating to an academic audience and it's vaccine safety trial data, et cetera, boy, you're going to have tables and tables of data. Fantastic. Put it in the appendix. Email it as a separate file. But for the presentation is what I'm talking about. You're going to communicate it more effectively if you do the things that I'm talking about here today. So markers are gone. I've simplified, reduced distractions once again. By the way, you may have noticed I made the lines a tiny bit thicker just so they pop a little bit more. All right, so next up, I look at these things and I say, okay, right now, this chart enables me to see if these two lines track against each other. One of the pre-attentive attributes of humans' perception of visual information is called parallelism. We're really good at tracking parallel lines. And so if I needed to compare the old technology, which is the gold line, to the new technology, the green line, and how they're doing compared to each other, this would be a good chart. But I asked the client, I said, do we need to compare them? Is that what the goal is for this? And they said, no, what we really need to know is how is each line doing against its own benchmark? Has nothing to do with the old versus the new. Good. I say F no to this chart type, or at least I want to just separate them into two separate charts. I can now much more easily see when the dotted line or the yellow line crossed the yellow dotted line, when the green one crossed its one, now that it's not a spaghetti chart all over each other. So again, I'm focusing the eye on what matters by simplifying, reducing, etc. Now, I'm looking at these two charts and I'm asking myself, and I said this before, I said the star of every chart is the data. And that's a good default rule. But occasionally, the star of the chart is not the data. And this is where you have to think about your quis and your quiant and those other things I keep talking about. What is the point of these charts? It's how am I doing compared to benchmark, which means it's not about the line, and it's not about the dotted line either. It's about that space in between. It's about how far back, how long have I been below that line, and how much below that line. In other words, I ask myself, is this even the right chart type, a line chart? And the answer is no. What I want actually is a new chart type, a deviating chart. I want to emphasize that space. So now all my color is gone, except now ridiculous choice, neon green, but really pretty attentively, you're going to look there first now. I'm helping you see the point of this story, right? This isn't about manipulating my audience. This isn't about bias. This is about telling the story that needs to be told with this data. So in this case, focusing on what matters and using color intentionally to help do so. All right, so now I look at this chart and I ask myself, all right, I've removed just about everything. The bars are gone. I've separated the charts. I've simplified, reduced color. Like, we're down to just about nothing. Is the story coming through? And occasionally, it's not just about do less. Occasionally, okay, now it's time to strategically use annotations, start to tell the story. Look here, this is what this is saying, right? Maybe, to my point earlier, are there numbers? Do I need to show the numbers? Maybe I should actually add the numbers back in. Just those two numbers, just the ones at the end. That's what matters, right? And a little typography here, right? I'm saying the data point is probably the number that matters the most. The benchmark, which has been the same for the last 9 months. We have a meeting every week. I probably don't need to emphasize that as strongly. So I'm going to make intentional decisions with typography to really help you pre-attentively see the important stuff, information hierarchy, and subdue the less important stuff, but it's there. I think you might need to be reminded occasionally of that benchmark. So I'm going to include it. I'm going to make sure it's legible. And you could argue maybe this is too small, especially with my two little tiny charts. Fine. We can have a good debate about that. So again, strategic labeling annotations and making sure the story is coming through. So 2 more changes. And the second to last one is a big one. Ready? Here we go. I look at this chart and I say, okay, am I telling the actual most important story here? And I asked the client, I said, okay, we got the old technology, we got the new technology. Tell me about the old technology. Do we care? And they said, well, actually that team has been disbanded. No one's fixing bugs over there. So the error rate, like we're not fixing those errors. So it literally is meaningless. So I asked myself, why are we showing it? F no to that one, get rid of it. This is the actual story. And I presented this to the client. They're like, oh my God, I cannot believe that we weren't doing it this way all along. Of course, this is the story. All the rest of the nonsense in that chart was absolutely useless. And again, by default, you can talk me into more complexity. I'm not saying everything has to be minimized, but your default should change to minimal because most people, that's their struggle. They put too much by default. If you just change the minimal approach and only use complexity when you must, you're going to do a better job communicating with it, pretty much just about every audience. So once again, removing unnecessary elements. And the very last change, and you can guess what my answer is going to be, I asked, do I like keys and legends, where people have to like bob for apples or look like they're watching a tennis match to figure out what color means what, even with just 2 colors in this case. You know the answer. I say no to that one too, and therefore I strongly recommend you use inline labeling when at all possible. Put a blue color, blue text next to the blue line that says what blue is, green next to the green, etc. When we do that, it makes it easier for people to track what the colors mean. People get less confused, especially when you have a bunch of stuff going on in any chart. So, long story short, I highly recommend you default to no, you do less in terms of your design, and these are all the lessons to help you do that. And your magic F no key, just remember my face and say, oh yeah, that guy, when in doubt, remove it. That's truly honestly the best advice that I can give you. And again, plenty of exceptions to that. But one of the exceptions that I live by is this. Don't be afraid to show more data. So the example that I like to use is this. I did a survey. I asked 1,000 people to rate a product on a scale from 1 to 5. The median was 3.8. Great. People kind of liked the product. That's like mildly interesting, maybe. But what if these are the actual results? Right? 400 people gave it a 5, they loved it, and then everybody else. Same median score. Or maybe it looked like this. 400 people hated that product, and then everybody else. Same median score. Sometimes just aggregating to the number is fine. Other times, giving this nuance to your audience. Again, think about your audience. Can they handle it? Are they interested in it? Is there an interesting story even in that distribution? Don't be afraid to show more data. They can handle it. But even in this case, I'm simplifying the design. Do less in the design, even if you show more data. Now, a couple of quick examples, I know I'm running a little bit low on time, is this. I just found this visual the other day. If the Earth was flat, this is what the entire Earth would be made up of. What could be simpler than this, right? I can easily see the proportional share of ocean, fresh water, built up areas agriculture. And obviously the story for this particular visual was about the built up areas in agriculture, because that's where the majority of the color focus is, okay? There's another one that came out just this past year that I absolutely love, the biomass of life. And actually, let me just click on this one real quick, because this is really cool. It's from Visual Capitalist, which does a lot of great data visualization, including science viz. And think about if an academic was going to go present this data at a conference, what that poster would look like. 8 million words, 400 footnotes, 47 charts and graphs, like all kinds of craziness, right? But this is a pretty simple data set, okay? There's a lot of species, and we're just measuring the carbon that makes up all of this stuff. And it's just the proportional share. They give the actual numbers, but it's just a proportional share. Now, you could say, yo, Bill, like, I'm looking at this and this doesn't seem like do less. This is heavily illustrated. This is three-dimensional. There's plenty of words on here. Yeah. But my point is that thinking about the poster that the person who came up with this might have wanted to present, stripped down, pared back to this, which by the way is a super beautiful, cool design, is really nicely done. And by the way, there's the context of here's animals, and then of course here's bacteria and plants and all the rest of it. So there's a lot behind this. This could have communicated in an extremely ineffective way. And even though this has some complexity in the design and the visual approach, really, this is a do less. This is a beautiful, simple visual experience that I think they just did a fantastic job with. So that is my presentation. All I want you to remember coming away from today is think about your whys, and by default, say no to everything. And then if you do, then you can strategically add stuff back in as needed, but start from the position of no. Thank you very much. I know we're doing questions at the end, so you can ignore this for now, but back to you, Nikki. Thank you.
Thank you, Bill. That it reminded me of Kill Your Dog.
Great. Well, greetings from Seattle. It's getting a little bit lighter here, so you'll see more of me as the morning goes on. I'm really thrilled to be here today with all of you and with all of the other panelists. I've already learned so much just in that first 20 minutes. So thank you, Bill, for everything that you shared. We're all here today because we sort of have a common mission. We're working to try to bridge a gap between scientists and often the people that they're trying to talk to. So I'm here to tell you a little bit about myself really quickly so you know where I'm coming from. And then I'll discuss with you the 3 S's of visual science communication. And my goal for you today is to leave here with 3 things that you can use today. So let's get started. I love art. I drew this picture when I was in kindergarten. Apparently I was way ahead on the purple hair thing, since this drawing is dated from the 1970s. And I've spent my life as an artist, but I also really, really love science. And so I've spent my professional life as an artist who works with scientists. And I spent a lot of my childhood outside in nature, but also indoors looking at books like this one. My mom was a nurse, and this is one of her textbooks from nursing school. And I would sit and look at this book for hours. I ended up studying science in college, but I also studied fine arts. And I had surgery my senior year of school, which kind of blew my world right open. And I was really rattled that my body had all of a sudden failed. And I was really touched by the surgeon who fixed me. And so that experience kind of brought me back to these images. And I enrolled in an MFA program in medical illustration at RIT in Rochester, New York. So just mention I'm a fellow New Yorker because Rochester is my hometown. And so medical illustration is really not that unusual, but there still aren't a lot of people who know about us. And we're kind of the guidance counselor's dream. It's the perfect career path for the student who likes science and art and really can't figure out which to choose. So I'm just going to show you quickly a couple images that I've done throughout the years. And there are many, many people who are interested in both science and art, as Nikki has indicated. And I've noticed a real increase in people who want to know how to do this, either as a career, but also as a way for them as scientists to communicate their science to a broader audience. And that's why we're here today, to learn how to communicate science more broadly. And so for those who don't go to medical illustration or design school like I did, and yet need to communicate about science, it can be difficult to find opportunities to learn about visual communication. And I found also that many people lack confidence and are maybe uncomfortable with making pictures or drawings of their ideas or their theories or observations. And I will just say that visual communication is not about being the best artist. It's really about understanding how we perceptualize visuals and how we can use that to help communicate better. So the good news is that we're all born visual thinkers and communicators. And you can probably remember making pictures as a child and feeling pretty comfortable doing it. And that's because our brains have extraordinary skills for processing visual information in order to understand the world around us. And so this is my son, who's now 11, but in this picture, he's 2, and he's just beginning to draw a picture of our house. Now, before you think we live in a geodesic dome, I have to say, sadly, we do not. But I use this image to remind us that as kids, most of us are pretty brave about drawing. We use drawing as a way to communicate and a way to represent something. So I'll tell you a quick story about how visualization, or the lack thereof, played a key role in the history of science. You might recognize Gregor Mendel, who was an Austrian monk who was also super into science and math. And he planted a garden in his monastery, and he kept careful records of his breeding experiments. And amazingly, in this garden, he developed the principles of our modern understanding of genetics. And he spent more than a decade working on the math, making all these mathematical proofs. And he had a once-in-a-lifetime chance to present his work at the Natural History Society. But he had a lot of complex math to explain, and to our knowledge, he did not use any visual aids. So Mendel's big moment was a failure. And I really like this cartoon here. No one in the audience understood his groundbreaking work. Gregor Mendel's brilliant work was dismissed, and his theories remained unknown until more than 15 years after his death. So you get the moral of this story, right? Scientific discoveries, no matter how promising, can't benefit us if no one understands them. And so the number of science pictures made by trained professionals like me is really very small. There is a lot of science out there, and there's very few of us trained medical and scientific illustrators. So if you think of all the journal articles and all the graphical abstracts and figures, and especially all of the PowerPoint slides, the vast majority of science pictures are really being made by scientists themselves. And so the title and topic of this presentation, The 3 S's, is from an online course that I co-created with a colleague and medical illustrator, Betsy Pele. And the course is called Spark, the 5 Strategies for the Visual Communication of Science. And we formed this course, and we formed a company called Picture as Portal, because we really believed we could empower people to make clear pictures that communicate their science through a simple course of training. And we really believe that pictures can be portals to understanding. So Spark is a step-by-step method to create a picture of an idea based on our years of experience creating those pictures. And we selected the principles that we thought were most effective to communicate about science. And so let's talk about letting go of literalism, which is one way to reach your audience and is one tiny part of the Spark method. So I'll show you 3 ways to modify your content that we'll call the 3 S's for short. All right, so buckle up, here we go. This is a photograph of a surgical procedure. It's accurate, it has a lot of detail, it's realistic, and it's literal. But imagine that you're a nursing student trying to learn from this photograph. It certainly falls short of an effective communication tool, but why? What's wrong with being so literal? Well, let's look at the picture on the right, representing the very same surgical field. How is it different from that photo? Well, it helps the audience, and we've heard that word before already, it helps the audience know what's important by being selective. It selects some things, but not others. It leaves out unnecessary detail like the skin, the incision, the fat, parts of the anatomy that aren't relevant, and a lot of blood. Now, being selective is not a new idea. This is one of the earliest known examples of a scientific illustration and was made about 20,000 years ago in a cave in northern Spain. So let's look at it in black and white so it's just a little easier to see. It's a picture of a mammoth, clearly showing the location of that mammoth's heart. And what's really interesting about this picture is how much the artist chose to leave out. The artist chose not to make the picture literal or realistic, but to select only what was absolutely essential, almost like a picture you'd see in an instruction manual. And in fact, if we compare this to a modern example of a surgical drawing made roughly 20,000 years later, you can see the same picture-making principles are being used. In both cases, the person making the picture selected what was most important and left out the rest. So our first S is be selective. When you have a lot of content, you can let go of literalism, of too much detail, and only select what's most important to include in your picture. And there are lots of ways to use this technique, and I'll show you just a couple more examples. Here's an illustration from Scientific American from, I think, the 1950s, and it shows the circulatory system. But notice that the head, lungs, and lower body are not there to distract us. This artist was selective. Years ago, I attended a presentation by the brilliant Amanda Cox when she was the graphics editor at the New York Times, and she talked about being selective too. She called the details that you don't choose to focus on the background singers. And I really like this way of thinking about the parts of a picture. So in this data visualization, you make choices along the top about your demographic to see the jobless rates shown in blue. But those gray lines are still there. Those are the unemployment rates for the demographics other than the one you're looking at. They're the background singers, but they provide context. In this series of pictures, there's a lot that could be there that isn't. You know, the entire background is removed. We don't see the hospital or the laboratory walls or doors. We don't see anything else on the cart in any detail. We don't see any details in that clothing. And most obviously, decisions were made to use color to be selective. So that blue is an undeniable signal that we should be looking at the object in each panel. So the person, the cart, the gloved hands, those could all have been removed in this case. But now they're shades of gray so that we focus less on them. They're kind of like Amanda's background singers. And sometimes you can remove almost everything. Sometimes an outline is enough for something to be recognizable. And according to some research done in 1957 by Ryan and Schwartz, often an outline is more quickly recognized than a photograph. This image is by the brilliant David Goodsell, showing a step in the coronavirus life cycle. And the interior of a cell is very complex. As we know, there are membranes and proteins and organelles and molecules and receptors. There's a lot going on. In this image, Goodsell is selective in that he shows the structures he wants to call attention to, his lead singers in color. And the rest, the background singers, are shades of gray. He could be selective and remove them entirely, or he could, as he did here, retain them, but be selective about their color. And as we saw before, being selective can definitely apply to data visualizations. The graph on the left is pretty typical output for something like Microsoft Excel. And the graph on the right shows the same data, but a lot of visual elements were eliminated, like unnecessary lines, data markers, tick marks, color gradients that make the tick marks look shiny, shadows, and even the legend in that box. So when you're selective, you can focus attention on what's most important, which is your data. And I just want to shout out to Bill for mentioning the y-axis orientation, so I don't even have to for this one. In this series from the Financial Times, we can see the death rates for COVID-19. In each of these small graphs, the designer selected the country's number to be the focus in blue, but kept some other details in place, like references to the rates for other countries. But they're in the background singers. Sometimes your content is so complex that being selective isn't enough. So for a long time, this is what arteries of the abdomen looks like in anatomy books. And the pictures are scientifically accurate and realistic and literal. And in this case, the artist was actually selective and left out some anatomy. He used color to show us that the blood vessels are the lead singers here. But in some ways, these could still fall short as a communication tool. So imagine you're a student trying to learn the branches of the abdominal aorta. For the first time, these pictures are so complex that they really obscure the pattern of those arteries. And so a more effective picture for learning might be a schematic like this. It's not literal. It's not a representation that it is a representation that emphasizes the pattern, however. So now what's most important is most accessible. So the second S is be schematic. When your content is very complex, be schematic. Make a diagram. This is especially helpful when you want to communicate patterns and relationships between things. So we'll look at a couple more examples. On the left, we see the structure of an antibody based on actual data. And I can say that I appreciate the color coding and the labels, but it's still very complex. There are wispy thin structures and domains overlapping in 3D space. And it's hard to get a sense of the shape and the symmetry of the molecule. And this might be okay for a molecular biology audience, but it is not the clearest picture if you want to be able to talk to a wider audience. And the schematic picture on the right really clears a lot of that up for us. The brachial plexus are the nerves running from the neck to the armpit. And even though the skeletal image on the left is selective, the skin, muscles, and organs have been removed. Being selective isn't enough. And the schematic diagram on the right is a clearer representation that highlights the patterns of these nerves. And of course, maps are great examples of being schematic. The satellite image on the left includes overlays of the subway lines, but the schematic diagram on the right is a lot easier to read. Unnecessary detail has been removed, the patterns are clearer, and the relationships between the train lines are easier to understand. Here's a favorite of mine. Charles Darwin's sketch from 1837 is the earliest known expression of his concept of natural selection and evolution. And to me, one of the most significant things about this image is his notation right here, I think. He made this sketch in order to clarify his thinking. And Darwin made this drawing to visualize a complex concept, but also to help him think through that concept. Now, sometimes being selective or schematic still is not enough. You may be presenting a concept that's very unfamiliar to your audience or very abstract. So let's say we want to explain how one molecule attaches to the binding site of another molecule. We could show a picture like this, a literal representation of what molecules look like and what it looks like when one binds to another one. Or we can make a picture that's symbolic, not literal at all, but using a metaphor of a lock and a key. Symbolic representations like metaphors are especially useful for communicating conceptual information. And so I've got some more examples of these, but as I go through these, I thought it would be fun to enter into the chat perhaps some other examples of symbols used in science, because I'm sure you know a lot of them. So this is a representation of the brain that you can see modeled in your own hand, but it works well as a visual depiction too. This is one I've seen a lot recently, maybe you have too, the Swiss cheese respiratory pandemic defense. Cells are sometimes described as cities, and the mitochondria referred to as the power station of the cell. So in some cases, it might help your audience to see pictures like these to better understand cellular complexity. And war is often a metaphor when used to describe the immune response to pathogens. And I especially like this one because it's so whimsical. And the COVID-19 artwork by Toby Morris and Dr. Susie Wiles, I'm not sure if you've had a chance to see their work from New Zealand, has been a recent favorite of mine. They've used several metaphors to communicate about the pandemic and public health in really approachable GIF animations. So I don't have enough time to show you much of their work, but I'll just give you a peek at a couple things. So here they're using a 4-lane highway compared with a winding road to explain why the COVID vaccine was developed relatively quickly when compared with traditional vaccine development. And here they use video game analogies like health points and cheat codes of bosses and multiplayer gaming to communicate to a young audience about the COVID-19 vaccine. They cleverly and adeptly address how vaccines work, why there are breakthrough infections in vaccinated people, and how getting vaccinated helps others, all using these really cool video game metaphors. So I highly encourage you to check out their work for yourself. It's really so innovative and approachable and easy to understand. So our third S is be symbolic. When your content is very unfamiliar to your audience or abstract, such as when a new concept is being introduced, you can let go of literalism and be symbolic. So since these are so fun, I just want to show a few more. This one is Brownian motion described as bumper cars. This one is CRISPR shown as DNA scissors. This one is the Higgs boson particle explained in terms of levels of celebrity. And sometimes different ways of representing may work with different people in your same audience. So there's nothing wrong with using multiple ways in the same picture. So this example was created for hand surgeons, and the wear patterns on the trapezium bone in the wrist are represented 3 different ways in the same picture. We've got literal, we've got schematic, and then we've got symbolic. So remember that a picture is always a representation of something. You have many choices available to you about what that representation will look like. Choices that can maximize the unique power of pictures to communicate. So I encourage you today to let go of literalism and make a clear picture that will be the most meaningful to your audience. So I'll summarize really quickly. The 3 S's in visual science communication. When you have a lot of content, be selective. When your content is very complex, be schematic. And when your content is unfamiliar or abstract, be symbolic. So that's it for me. Thank you so much. My email address is here. If you ever have any questions after today, I am always here to talk about this topic. I know that was a lot. If you'd like to know more about the Spark course and the 5 strategies, the website is pictureasportal.com. There's some free videos there. And then if you're interested in taking the course, I can offer a discount for attendees today if you use the code BASICS through this weekend. So thank you so much.
Does that look good?
Yes.
Let's see. You see my main screen, right?
Yes, it's a wonderful coronavirus that looks like
All right, thanks. So yeah, I'm Gary Oberbrunner, and thanks so much for having me here. It's really an honor to present with such great folks. I spent the last 20 years doing visual effects for movies and TV, created some cool visual effects software. Before that, I did visualization on supercomputers. And so with my new company, Dark Star Systems, I'm creating web-based tools to help scientists create beautiful videos of their data. And by the way, I grew up in upstate New York. I'm in Boston now. I wish we could all be there in person today. So today I'll tell you about visualizing scientific data using video. Let's see, wait a minute, here we go. So my talk will be in 3 parts. We'll do an overview of what scientific visualization is all about. We'll talk about video and the language of film and how to put those parts together so you can create your own sci-viz videos. So visualization, which I define as the art of turning scientific data into imagery, is just a part of scientific communication. And this goes back a lot of this to what Bill was talking about. Sure, visualization is an important part, but it has to start with a story, just like in movies, right? Cool visuals don't make up for a lame plot. So we'll focus on visuals today, but don't neglect the storytelling aspects. And I'll put some links at the end of my slides if you're interested. So the main goal of visualization is to help the viewer see what's important and interesting about your data, to communicate insight. And of course, a secondary goal is to make your presentation more interesting. Video and imagery draws people in and makes them pay more attention. So we'll talk more about video in a few minutes. But my 3 key principles for effective visualization are to know your audience, know your goals, and know your data. So let's talk about each of those things. First of all, what kind of presentation are you giving? Is it to a group of scientists? Is it to an investor, a funder, a journalist, school children? I've found it really incredibly helpful to answer the questions on this slide as I think about doing a scientific presentation, because they help jolt you out of thinking like a researcher and into thinking like a storyteller and empathizing with your audience. And that's important for any story, right? You have to think about what they're ready for, what you want to communicate. And the key question is the last one here. What's the one sentence message that you want them to remember? And that brings us to understanding your goals, right? Before you start into visualizing data, you have to know why you're doing it. Are you trying to inform, explain a concept, entertain people, inspire them, provoke discussion? And I'll say that often visualization is done early in the pipeline. So you explore the data as you're doing the research and you discover insights as you go, and that's great. But more commonly, it's an afterthought. It's done as part of presenting your work. So ideally, I hope you'll learn to think visually all throughout the discovery process. And if you do that, beautiful visuals will be a natural result. So what do you want to show with your data? Do you want to show form and structure? Typically, if you have a single data set that's 3-dimensional or 2-dimensional, this is an appropriate kind of goal. You could get things like surfaces and volumes and images and slices. But maybe you want to show relationships. You want to compare and contrast. You want to reveal data that's hidden within a larger context. If you have multivariate data or simulation versus experiment, you often want to highlight the relationships. And then finally, if you have process, motion, and animation, those all involve time. And there, of course, video is the natural medium for showing for showing your data. And the third principle that it's important to keep in mind, as Bill said, is to know your data. The deep understanding of your data allows you to visualize it effectively, to bring out what's important so that it shows the key idea rather than having to walk people through it and tell them. One easy way to categorize data is by dimensionality. If you have one independent variable like X or time, go with graphs and charts and spark lines. Those are like the little stock market tickers that you see, or icons. Keep it simple. Don't gussy up your data just to make it pretty. You want to, as Bill said, say no to all of that chart junk. If you have 2 or 3 independent variables, typically it'll be spatial, but I put spatial in quotes because nearly anything with 2 or 3 independent variables can be made spatial. Then you have images, maybe they're pseudo-color, maybe they're height fields. You can show them as contour maps or streamlines. And we'll look at examples of all of these things in just a minute. If you have 3 spatial variables, then you get into volume rendering, isosurfaces, streamlines. And then when you add time as a 4th variable, then it naturally becomes video. And of course, with any of these, you can have 1 or more dependent variables, and it's perfectly okay to overlay different techniques to help your audience see what's important. Now, beyond spatial data, you've got specialized data sets like atomic structures, irregularly sampled data, and multigrids. There often are standard tools or custom tools in your domain to help regularize those and turn those into things that you can then turn into graphics. And we'll talk a little bit more about that in a minute. Now, once you get into really abstract data like graphs, degrees of connectivity, network structures, lists, that becomes more information visualization than scientific visualization. And I'm not going to talk about that so much. I'm thinking about sort of data heavy visuals that you want to present to sort of simplify a large data set. So, so let's look at a few examples. We'll give you a short tour of just a few to whet your appetite. So this is Menard's famous map of Napoleon's approach and retreat from Moscow, courtesy of Edward Tufte in his visual display of quantitative information. It's an incredibly information-rich infographic without being cluttered. It shows the location of the army size as the width of the line. It shows time, geographical references, temperature along the bottom, referenced to where they were. It tells an incredibly information-rich story that you can read at a glance. Now, I don't expect your scientific visualizations to look like this. I mean, this is more of an information visualization, but but hopefully will inspire you to keep things simple and make your visualizations dense but clear. So here's a simple 2D GIS data set shown as a 3D model using elevation as height. It's got a couple of dependent variables. We've used the height to create a height field that gives you the 3D model. And it's also colored by land use. So you've got the blue for the water and the green for trees and the white for snow. And it also has isosurfaces of height, commonly known as contour lines. So you can see all three of these visualization techniques at once in this 2D data set. Here's another simple one, sticking with 2D. We've got two dependent variables, wind velocity as a vector, and I think pressure as the color. So the wind velocity is visualized with the streamlines along the vector, and then the streamlines themselves are colored by the pressure at that point. And this comes from UCRL at Lawrence Livermore Labs. Now, getting into 3D, this is a visualization of a Rayleigh-Taylor instability in the interface between some fluids. And here you see an isosurface, probably of density, to make the top and bottom surfaces visible, and two slicing planes, so you can see how tangled up and convoluted the fluids get. I think this one's particularly beautiful, largely because of the color scheme. But just imagine how much cooler it would be if it was in motion. And so this one is also a 3D data set. It shows so-called direct volume rendering. Each voxel or data element in the volume is given a color and an opacity. So it gives a look like abstract clouds. And we'll take another look at a real-time version of this in a little while. This is a really good technique for showing complex interior structure in a data set. And it's also often used in medical visualization, like for CAT scans. So this is more like my own current work. I'm doing a lot of molecular visualization now. We start with 3D coordinates for each atom within the molecule, and then we build a 3D ball and stick model of the molecule colored by which element it is. And then on top of that, there's an opaque isosurface. I think it's electric potential probably around part of it. And we color that by another dependent variable. I'm not sure what that was in this case. So there's some examples. But once you have your data and you have an idea of how you want to present it and you know what you're going for, if you want to do your own visualization, you'll need to follow some variation of this path to get your data into visual form. You'll very likely have to pre-process it using something like Python or R or MATLAB to get it into a visualizable form. Then you'll apply some visualization algorithms like isosurfacing or coloring to turn the data into graphics. And then you'll render the resulting graphics into images or video. Then take a look at what you've got, admire it, learn from the results, and go back and repeat and improve it. So now let's take a different tack and look at the language of film. So film is an unspoken language that we all share. Like a spoken language, it has syntax and grammar, but the elements are things like color, light, composition, staging, action, mood, editing, sound, and music. Film itself is less than 150 years old, and modern film is really only about 70 years old. But in that very short time, it's become central to our storytelling worldwide because of its high bandwidth, its multi-sensory nature, and its tremendous capacity to elicit an emotional response. And interestingly to me, it's not obvious why a set of flickering still images, quick cuts and odd camera angles and sudden shifts, why should that even work? Why is that so compelling to us? Why aren't those quick cuts disorienting? Part of the answer is we've grown up with this language and we respond to it instinctively. But another part of that answer is that it works because we're always editing our own perceptions, everything from eye blinks to zoning out during the morning commute. We naturally chunk our memories and our lives into these shots. And so film mimics what goes on in our natural perception. So in the creation of a movie or a commercial, right, the creators bring all of these language elements into play in the service of telling a story, or hopefully in the service of telling a story. They use color and lighting to create interest, communicate mood, and clarify structure. They bring all of these elements together into a coherent whole to make something visually, auditorily, and emotionally compelling. And I won't go into all of the details here, but you get an idea of it. And in a full video creation pipeline, there's a lot of complexity. You have to create a storyboard and a script, then you shoot the content, edit it, add titles, and deliver it. Even for creating a short commercial, this pipeline can be very involved and time-consuming and expensive. But the good news is that for a scientific video, you don't have to go through all of this. You can cut to the chase very, very simply. And so that's what we're going to talk about next. So how can you create your own scientific videos? My number one recommendation to you as a science practitioner is keep it simple. In a scientific presentation, keep your video short. It can still be an important part. It can be just a single shot as an intro or a conclusion or a highlight. Just clarify the most important concept. If you keep it to a single shot, you avoid the need for all the storyboarding and the editing and the music and the post-production, and it keeps your script really simple. So use one or two viz techniques, one camera move. As Bill said, say no to all the rest. One color scheme, keep your animation simple. And I'll tell you that creating a short animation as an adjunct to your presentation makes a great social media post or update for your website. So let's look at a couple of video examples of animated scientific visualization. First one on the left is a volumetric data set of the Pacific Ocean with an isosurface marking the places which are above 0.5 degrees over the normal average temperature. So it shows the development of an El Nino. The color represents the depth below the surface because they want to emphasize how deep the temperature gradient runs. And you can see how it develops over time, starting in the south and growing northward. The second animation, which I think is really cool, is from an experimental data set where they photographed bubbles moving in a chamber. They tracked them and then developed that into a complete flow field with velocity at every point in space. Then they visualized that with these cool hairs or streamlines. And then they changed that into a set of isosurfaces of velocity to really elucidate the structure of what's going on. So how can you make videos like this yourself? And I won't lie, creating video is harder than just creating still images and graphics. But it starts from the same place. You'll want to use a specialized tool or custom code to transform your data into a standard format. Often people use Python. I'm a big proponent of that. There's a huge number of libraries available for Python to transform your data into beautiful graphics, SciPy, PyPlot, VisPy, VTK, and so on. but use what you're familiar with. If you know R or MATLAB, just anything, please, but Excel. Use what you're familiar with. Then once you have some 3D graphical data coming out of your data pipeline, I suggest using Blender for 3D graphics. It's an amazing tool. It's totally free, open source. It's rapidly improved in the last couple of years. If you tried it 5 years ago, it's totally different now. And it can do a tremendous amount. But on the other hand, if you have access to Houdini or Maya for creating 3D graphics, totally go for it. Those are used in a lot of high-end sci-viz projects. When it comes time to editing your video, a lot of people use Adobe Premiere or Final Cut Pro, but Lightworks and OpenShot are free alternatives that are totally fine for doing simple video editing. So what kinds of tools can you use to create motion graphics from data? If you just have animated images, like a time sequence of data, just create individual still frames and collect them together like a stop motion animation. Final Cut can do that, so can Lightworks and Premiere. If you have 3D data, you'll need to create polygons and lines via isosurfacing or streamlines or height fields. There are a bunch of standard formats that are in common use, and you can probably find a library for your Python or whatever language you use that will help you create those and export them. In fact, a lot of these now are available to view online in web browsers. If you want to get into direct volume rendering, Blender and Houdini can do this, even with animated volumes, which is becoming super cool. I suggest using OpenVDB, but there are also plenty of other formats. And let's just take a quick look at an example of real-time volume rendering in a browser. This is just something I ran across on the web. A guy named Roland Ritz did this. And this is just a demo. You can't import your own data, but this is all running in real time in my browser with a volumetric data set, and you can dynamically adjust the opacity and the color scheme. Yeah, I think this points the way to the future for sure. And if you wanted to, you could just take a screen recording of something like this, and it would be a perfectly fine video addition to your scientific video. Let's see. So there are also specialized tools that you can use, like YTini, which is a Houdini interface to YT. That's developed and used by NCSA for their incredible cinematic scientific viz work. Definitely check out Kalina Borkovich's work there next time you're at a planetarium. It's open source, and if you're an Aero Astro, definitely that's the tool for you. BioViz Studio is the tool I'm working on. I created it for making beautiful videos of molecular structures. And I try to encapsulate and automate many of the film techniques I mentioned earlier, like using artist-created backgrounds and camera moves and using Blender behind the scenes. So this video is one I just created the other day with showing the action of molnupiravir, new antiviral drug causing mutations in SARS-CoV-2. And I'm interested in extending BioViz Studio to other scientific domains. So please see me afterwards if you're interested in collaborating on something like that. So how can you get started doing this yourself? My #1 recommendation, keep it simple. Use video sparingly at first. Start with Python and maybe Blender. Make a couple of tests. That they both have excellent supportive communities that will really help you out. And don't forget to work with your university's science communication department. They have access to all kinds of tools, tutorials, ideas they can hook you up with. So take advantage of all the resources that are available to you. And lastly, there's nothing as much fun as creating beautiful imagery from raw data. So have fun. And I'll leave you with just a few references. There's a few online tools that will help you pick good color schemes. Here are some of the viz tools that we talked about. And I'll leave you also with Pixar's 22 Rules of Storytelling and a couple of other resources, including Franklin DePace's Visual Strategies book, which is great. It goes through a lot of case studies like what Bill went through in terms of how to improve your visualizations, and of course Tufte's classic on information visualization. So that's my presentation. Thank you very much.
Hi everyone, it's a pleasure to be in such a great company here with Bill, Tammy, and Gary. Thank you, Nicoletta, for inviting me, and for Columbia University hosting us. I'm joining you all today from the state of Maryland in eastern US. I'm located 30 minutes outside of Washington, D.C. I sincerely hope you're all doing well. I'm sending a big hello to all the webinar participants, and especially I hope you're doing well during the pandemic, and we will come out of this together. Also, I hope the talk will shed some light to our group's efforts and bring also hope for the future of these. I'm happy to answer questions at the end of the talk. Okay, let's start. NASA's missions, engineering accomplishments, and scientific findings have inspired generations and advanced the world we live in. NASA's data are acquired by various sources, including satellites, robotic missions, and field measurements. NASA's research is bold, reflecting tireless efforts to ensure data continuity, efforts that span over decades. The ongoing research and applications aim to address some of our world's greatest challenges and our deep quest for knowledge by piercing into the past. And all these findings are reported back and shared in the world we live in. This is what I call the world as we know it. In this slide, we can see a collage of NASA science news just maybe from 1.5 weeks ago. Topics ranged from JWST, the James Webb Space Telescope, and its status as it's now in French Guiana. The launch date of JWST is looming closer, bringing such excitement for the scientific community and for the future. Then on center, we can see the minimum sea ice, some Arctic sea ice minimum. And on the right, the news about NASA's Landsat 9 mission launch, which represent one more effort of NASA's continuity mission to monitor Earth's landscapes. Now, let's take a closer look at just one of these major announcements, the Arctic sea ice minimum, and the materials that supported the NASA press release. The release is supported by visuals generated by the agency, a visual starting point that can engage so many more, that also serves as a confirmatory and explanatory media for our changing planet. Let's take a look. The role of science is not complete until its results have been communicated to the public. NASA's science storytelling team aims to fulfill that critical role by engaging and informing the public about the latest research findings and engineering accomplishments. Based at NASA Goddard Space Flight Center in Maryland, the team covers all NASA science teams such as heliophysics, earth science, planetary and moons, and astrophysics. The team comprises of subgroups including producers, science writers, social media experts, conceptual animators, and also the scientific visualization studio, My Home. Even though we cover all NASA science themes and hold years of institutional knowledge, it should be noted that our studio has advanced experience with Earth science data and therefore Earth system science phenomena. So how about we take a look at the few examples of our work only from last year, and as you watch the samples, please remind yourself that each work is solely data-driven. Scientific visualization is used from different audiences and for different purposes. Scientists use visualization to validate, analyze, or error check their own data. It's part of their daily research data analysis. A scientist may also create visualizations, or another expert, for publication in academic journals or for presentations to their peers and other experts, basically as part of their outbound communication. So now we see a shift from the private realm of the self and the science team to the public realm. The third and final audience is basically scientific visualization for the general public, non-experts. These different audiences require different treatments and consideration to be taken from the very beginning of the visualization process through to the packaging and distribution of the created content. Our studio, the Scientific Visualization Studio, creates content that actually serves both the scientific community and the public, a practice that presents its own challenges and accomplishes this with cinematic scientific visualization. So let's talk a little bit about the scientific visualization studio practice and define what is cinematic scientific visualization, which is the field of production quality computer animated storytelling that is based solely on data. The impact of these movies stems from creating visual representations of most often data with an inherent structure that is invisible to the naked eye, and such movies allow us to perceive data and therefore science in otherwise impossible ways, in impossible scales and perspectives. And thanks to such productions, we can see satellite orbits, solar flares, climate phenomena. Cinematic scientific visualization focuses on using Hollywood storytelling techniques to communicate scientific findings and phenomena to the public, while upholding scientific integrity and data accuracy. Visualization productions of this kind is a distinct and niche practice within the communities of computer graphics, visualization, and production. And even though it's a niche field, it has a rich history of its own of almost 50 years in the making. Such productions require the collaboration of a scientist, a visualizer, a producer, and a science writer. And the method that we use is what I call the iterative approach. You feed in data, in parallel you craft the story with data and sketches, then start creating drafts, share the work, receive feedback, and then improve, correct. You might have to feed in other data or change your sketches and your storyboards, share again and materials for review till the final approval is reached. Aside from having deep knowledge in earth science, heliophysics, and lunar science, we bring also expertise on fusing multiple data from multiple sources, and this basically means layering multiple data with varying temporal and spatial resolutions. This layering, which is very similar to painting, as you layer a painting with maybe more than one figures, or how you create an orchestra out of individual instruments playing, allow us to create complex visualizations with context. The visualizations are created for multiple resolutions depending on the venue or platform they will be shown, and we support HD, Ultra HD, hyperwalls, and less often bigger productions such as dome shows. It is a craft of its own, and we use a toolbox. The toolbox that we use basically storyboarding, sketches to create a storyboard. We use animation tools just mostly to create the movie timeline, such as Maya and Houdini. For rendering engine, we use Pixar's Renderman or Houdini's Mantra and in-house shaders, as our work requires high precision and capabilities that are not supported by typical movie making software. To register data, we use IDL, Interactive Data Language, in-house scripts, and commercial software less often. I would say more often open source. And to process the data, we use IDL again, and programming. Now, it is important here to mention that using IDL, the Interactive Data Language, is a great tool for us because this is also a tool that is widely used in the geosciences. So this way, we develop immediately a common language with the scientists that we serve. So, for example, we receive their data, we process them in IDL, and we can quickly share drafts as we process the data and tell them, look, this is what I see using IDL. Do you see the same? All visualizations are vetted by scientists for accuracy and scientific integrity, and we see our work as an integral component of the journey of science, and that can mean many different things. But for example, background or genuine interest in science is helpful. And also it is important to understand deeply the venues the scientists present or how they present, along with the needs of the general public. Now, once the visualization is complete, like the one that I showed earlier, the one about 2021 Arctic sea ice minimum, then the products, the visualization and related products are released through the SBS website. And the best way to describe the SBS website is, or the way I like to describe it, is a public-facing mega database of all sorts of goodies, visualization goodies. Currently, it's hosting over 8,300 entries. For example, here on the left, you can see the homepage of the SBS studio. And then on the right, you can see the individual page where we are releasing the visualization and related products, visualization products to the Arctic sea ice minimum. Now, it is important here to mention that there are related products because we have different versions, maybe one for the scientific community, one for the public with narration and text and annotations. So all these are available to the public, and we also release additional movies in various formats and frame rates, along with the frames that actually constitute the visualization. All material is openly and freely accessible to the public, and we simply ask to provide credit to our studio if possible. And since content is freely and openly accessible, then it may take its own life, take a life of their own, thanks to the broader community, the scientific community, museums, news outlets, educators, filmmakers, documentarians. And here we can see a couple of examples how, for example, a visualization was used on a visual created by New York Times, and then some visualizations were included in the documentary called Connected from Netflix. Now that we have seen a high-level journey of scientific visualization productions, I would like to share a few thoughts on the future of our practice, especially since there might be graduate students or future data visualizers in this group. And I'm going to take my NASA hat off, and I'm going to share this as an individual practitioner, as I often find myself thinking about the work, reflecting on the challenges, what works and what does not. So even as we may contemplate the next era of visualization, there is significant value in comprehending the ground covered the past 3 to 4 decades. Of course, we cannot do this in the next 5 minutes, but looking back, I would like to share 2 foundational texts and an effort that marked the field's beginnings. In 1977, John Techi's impactful publication defined the approach of exploratory data analysis, what is known as EDA, and provided techniques and guidance on how to explore data. I find the description from David DiBiase in one of his publications on Spot. He describes the work more than a collection of techniques. He calls it an attitude, the willingness to look for what can be seen, whether or not anticipated. And in 1987, Tom DeFanti, Maxine Brown, and Bruce McCormick penned the NSF-funded panel report on visualization in scientific computing. The seminal report defined the field of visualization, described as a domain, identified the opportunities, and predicted the looming challenges for the next 20 to 25 years. So if you're new entering the field, or if you're teaching a course, I urge you to read it, recommend to your student, as it will give you an appreciation of what has been accomplished. And thinking about progress and starting leaps, my mind goes to Dr. Larry Smarr, who in 1977 was trying to visualize the collision of 2 black holes in 3D space, and was able to do that by building a physical model from papier-mâché. Now you can see that in a recent photo on top right. He then led the initiative that formed the National Center for Supercomputing Applications that eventually served as a home base for Donna Cox's team, Renaissance team, who defined the field of cinematic scientific visualization and who produced a series of works, including the collision of 2 black holes. So here you can see a fantastic circle closing. And one of the differences between now and the 70s and the 80s is that the field is not new and the problems are getting harder and more complex. Visualization will continue to be part of the story of science and is already embedded in other stories with societal, educational, and cultural dimensions. Therefore, there will be research and development to support exploratory, confirmatory, and explanatory visualizations, or even ones that lay beyond or between these worlds that we do not have the vocabulary yet. There are open challenges for our field. Exponential data size growth and the increased need of computing resources along the need of authoring tools are open challenges. But I'm not worried that much about these. There will be research and development on these with time. The challenges I want to focus on today are the challenges that may lay aside the strict academic barriers that fields and academic institutions build on purpose and requires us, the visualizers, the creators, to consciously engage and participate in two sets of praxis: transparency paired with openness and synthesis. And in reality, if you think about it, it is quite challenging to establish and even more so teach them, as they might be viewed more like social investments and cultural accomplishments. And these are also the praxis that are critical in shepherding the next generation of future data-driven storytellers. Over the years, I have gained a tremendous appreciation of the practice of transparency and openness directives within NASA regarding data and to the process by which visualization products and productions are released to the public. So based on these practices and the importance of data biographies and data provenance, I would like to propose the following framework for scientific visualization productions. This framework aims to promote transparency and openness for the visualizations created. I see this as an integral practice of a visualizer. The practice of creating a scientific visualization or a visualization and its release to the world is one. It's not separate. And when we reference the source, make it publicly available along with the visualized products, we support reproducibility and give the opportunity to other techniques, other interpretations, and serendipitous discoveries. For example, data journalism, a flourishing field, and citizen visualization can play critical roles by teaching the public and especially students from an early age how to read and question sources, how to read and question the derived data-driven visuals, and the meaning they convey. Transparency is also important as we need to illustrate limitations of data, the data assumptions, because we make assumptions when we create these visualizations, and uncertainty. And it might be the case that the sectors or the arenas that we operate or practice do not embrace these two practices and these praxis. So there might be intellectual property issues, or they might not be institutional values. But just imagine the impact if these were values adopted by our practice, our field, and sectors. And now let's talk a little bit about synthesis, which is basically about blending disparate information and knowledge in ways that yield novel insights. It is a distinct form of research and practice and can take across disciplines and professional sectors. Synthesis is at the core of innovation, pushing boundaries, and within our practice, it allows us to reach for better. And within sci-based production, better can mean functional through technology, accurate through science, and appealing through art. And the visualization of information and of science is about the need we have to produce a visual version of the truth. We are always after better, more efficient, effective, and relatable ways to present the truth, the core reason behind the evolution of visualization. And this requires us, the visualizers, the creators, to act as synthesizers. And as I'm exploring some of the open challenges on developing visualizations, I still see an untapped power source that the field still needs: the artists, who have the formal or informal training and talent to consciously see, hear, and craft messages, and carry these messages to much wider audiences and find people where they are. Artworks have the power to invoke our senses and craft memorable experiences and shape our world. Over the years, I had powerful encounters with artwork that defined my language and shaped my visual thinking. So apart from the impact and the influence artists had and continue to have on technology and the sciences and the field of visualization, there is something else that comes through art: the extrasensory. To give an example, I will share a personal story. It was 2005, a Sunday afternoon, and I was walking through the galleries of the Museum of the Art Institute of Chicago. I clearly remember entering a hall, and all of a sudden, a 25-foot tall sculpture was floating above the window-lighted Morton Wing staircase. It was a fabricated model of a real iceberg, sighted off Labrador in 1998, that Inigo Maglano Valle, one of the great artists in our era, constructed between 2003 and 2004 based on topographical profiles. To this day, this encounter, which spurred my interest in data visualization, still embodies for me the iceberg concept, despite having watched in awe a real-life one floating in a lake in Patagonia. The field of visualization has been learning from the fields of art and design and applied arts for many years. Since it's a domain that is currently being taught either in the sciences or in the arts and design, we might have to rethink how it's taught. This will require us to incorporate computational thinking into the arts-based education and visual thinking into the science-based program, but not as an afterthought for a few elective courses here and there, but purposely with the development of new integrated programs. And if we would like our audiences to be visually and orally literate so that they can understand what they see and hear and be critically minded, we should push towards incenting visual thinking and data literacy in K-12 education, similar to the effort of achieving writing literacy. As visualization experts, it is part of our practice to simplify and clarify and guide our audiences to the messages and truths revealed by research and data. And since the problems we are called to tackle become increasingly complex, this might require us to explore and develop new ways of doing, which will ask our audiences to respond with new ways of seeing. Thank you.